Okay. So let me take care of some small things. So now the thing is that ARM designs a new set, a new set has like, more instruction than the previous set, right? Version 8A has like, many more instructions than version 7. Version 8 was the first one, which was 64-bit. So version 8, ARM architecture version 8 onwards, or, including version 8, it's a 64-bit. So now you can imagine that, ARM is going towards server and desktop segment. And, as you know, that Apple is already using this ARM version 8 to make its M1 and M1X and, whatever they call it, M1 Ultra chips. Ones below that, version 7 and below, they were 32-bit because, initially it was developed for microcontroller applications or, small embedded applications. Now, everyone tells ARM that, there are certain instructions, which are very useful to us. So, put them in. So ARM does get a lot of input from design houses, not manufacturer, but design houses. Now, the second thing is that, ARM sells two things. It is making it say latest one, let's say not very latest, but, ARM Cortex A77 or A76. I have forgotten the number, but, let us just assume it is 77. This is like, top of the line for your mobile phones. It would sell this processor in two ways. To most of the people, it would give this design file as hard macro. So that means they have created this chip and prepared a design file. So, your processor, ARM processor details are hidden in here in this design file. All it would give you is hooks, that these are the input hooks and these are the output hooks, right? Everything inside, we have carefully laid out, we have done all the due diligence. So when you send this, your SoC, like, I told you that, your SoC is a big thing, system on a chip. It has your processor, and processor, as I showed you, takes up only this much part. Then, then there is a baseband processor, so which is your modem, which catches the signal. Then there is so this is your modem. This is your processor. Then, then there is a camera. There is like now latest is AI, ML chip. And, then there are sensors. So no one manufactures everything themselves. So what people would do is, say MediaTek, it would buy processor from ARM, and ARM would give them this design saying that, we have already laid it out. We have already written the RTL code. We have laid it out and we have created a file. We will just give you input and output details. And of course, certain timing details at how long it would take for an input, which is put in from here, to come out on the other end as an output. How long will it take? So that information would also be given. So those guys would be putting it in here and then, connecting it with other things. Companies like Qualcomm, they make their own modem. They also make their own processor because, they have architectural license. So they don't have to buy something like this. They can make their own RTL. Only requirement for that is that it should conform to ARM version 7 or ARM version 8 or whatever version they are using. So only top 3 or 4 companies have this architectural license where they don't have to purchase RTL from ARM. So Qualcomm is one, Apple is another, Samsung, TI, and, maybe a couple of more companies. The rest of the people have to buy this. So this is number one. So when ARM is selling this, its area is fixed. Now, what happens to the secondary users like Qualcomm that, they say that, we have in our total SoC design, we are given on our circuit, we are given this much space for ARM processor. Now, if ARM comes up with something like, design layout, which is something like this, then they would say, oh, this is not fitting in. We need something like this. And, then, manufacturers would start complaining. Qualcomm, Apple, Samsung, they don't complain because, they are making their own design. They are just making sure that it is compliant to ARM version 8 architecture. Other than that, they don't have to worry. But, the smaller ones like MediaTek and others, they buy something like this. And then if ARM suddenly change the shape of the layout, because they may say some circuit is here and then other circuit is here, then they would complain that, then, all the other parts of our design would be disturbed. In electronics industry, time is of absolute essence. If you don't come out with a new product by October, in US, maximum sale is in the US. And, maximum people buy things for either Thanksgiving or Christmas. So Thanksgiving comes usually the end of November. So end of November to end of December is the ultimate period when people buy lots of things. Just like, here we buy things on Diwali, they buy it there on that time during that 1 month. So if your product is not ready by that time, then everything is gone. So Qualcomm has to come up with its new SoC by say June or July so that other phone manufacturers can incorporate Qualcomm's processor in their own phone, and end product can come out in the market, or the new model can come out in the market by October period. So you can see that now a lot of people are making announcements. Like Apple has already made announcement that new products are coming. So that is the thing. So this is the answer that, whether manufacturers are consulted or not. I gave the answer that, design houses are consulted or not. For manufacturing process, manufacturers also has certain rules. So those rules would be given to ARM or companies, who are using it for say TSMC. If ARM is using TSMC, TSMC will give certain rules to ARM that, your design has to conform to these rules, only then it can be manufactured. So it doesn't work that way that, ARM gives a design and TSMC says, oh, this is too complicated. If it conforms to the TSMC rules, then, TSMC should be able to make it. Does that answer your question? Okay. Next one. Before we go to AMAT, I want to just clear one thing. See, till now you're talking about memory hierarchy. And, we are saying how good it is that, this is your processor. And then, processor goes to L1 caches. So this is instruction cache. This is data cache. This is L1, so level 1. And then, there is a unified cache, which is larger than this. We call it L2. And then, let's just say there are only 2 levels, and then it goes to a very huge main memory, which is somewhere over here. And, as a rule of thumb, we say that, if you find it in instruction cache or data cache, if you find the instruction in instruction cache or data in data cache, you don't have to lose anything. You can just get the answer in just one cycle. So, that is great. That is what you require. Okay, so now, but the problem is, if you find it here, you can do it in one cycle, but if you go here, it will take 10 cycles. And if you go here, it may take 100 cycles, just suppose. So this is like 100 cycles to go from here to here. Now, this for more, and you may say that 95% of the time, or more than 95% of the time, you will find whatever you are looking for, either instruction or data, you will find in this first level cache. Whatever goes in here, so that 5% of the instruction or data which has to go over here, out of this 5%, again 90% you will find over here. And 90, so 10% of 5% means 0.5% of the time you'll have to go all the way to main memory. So this, if you are using a laptop or a server, you can say, okay, it's a good deal. I mean, most of the time my work will be done very fast. But then there are certain applications which are known as real-time applications. And this is important because you may have heard this word a lot of time. Real-time processor, real-time operating system, and real-time program. So I mean, what is like, how do you make a real-time processor? So in real-time processor is a processor which is not necessarily faster than your general purpose processor, right? So your general purpose processor is what you use in your mobile or your laptop or your server. It is known as general purpose processor. So real-time processor does not have to be faster than that. In fact, most of the real-time processors are slower. Only thing is that they have to guarantee that work would be done or this program will be executed in certain number of cycles, right? So that is an absolute deadline. So these things are used in industrial applications, medical applications, where timing is of most importance. So they say that, I don't like this thing that, you say that, my program may be executed in just, if it's a 20-line program, maybe it is 95% of chances are that, it will be executed just in like 20 cycles, 20 instructions, 20 cycles. But in rare cases, it may go here where it would take 10 additional cycles, and here it would take 100 cycles. So you may say that, 20-line program or 20 instruction program may take 20 to 200 cycles. I mean, this is a rarity, but most probably the answer would be closer to this. But in some rare cases, when you keep on getting all misses and you have to go all the way here, it may take up to 200 plus cycles. Not every instruction is a miss, but say at least 10 instruction out of them is a miss. Then it would take up 200 cycles. Now a critical application would say, this is not allowed, right? I mean, I want a definite answer. So, for example, a car manufacturer would say that the airbag, for safety in cars, they are giving airbag. Now, airbag should be deployed in say 30 milliseconds, right? So if it doesn't deploy during that time, then a person may die. So as soon as there is an impact, kind of a sensor of, basically it's an accelerometer. So your car is going fast and suddenly it decelerates to 0. So that means the sensor would send a signal, and signal would be sent to two chemicals. I mean, they are filled in two pouches, and the pouches break, and two chemicals get together, and that creates an instant reaction, and it blows up, and it creates gases, and that would instantly inflate the airbag. So that is how the airbag operation takes place. So the manufacturers would say that you give me a surety that you will be able to do this in 100 cycles all the time, right? I want a hard deadline that it should be done in 100 cycles. I don't want it to go to 200 cycles, or in worst case 2000 cycles. I also don't care if you can finish it in 20 cycles. I don't want that fast an operation, but I want a guarantee from you that it should be done in 100 cycles. And this is known as a hard real-time system, which says 100 cycles, and it is absolute a hard deadline. There are also soft systems which say, okay, 100 cycles most of the time, but maybe 1% of the cases, if it goes to 105, 110, it's okay. But right now, let's concentrate on hard deadlines. So what people do is, for hard real-time processor, they have this processor here, and then there is, you would have guessed by now, is a single memory structure, right? So access time is always fixed. It will take definitely more than the cache would take. Say here, each access is taking 10 cycles, right? As opposed to one cycle if it finds the data over here. But any data or any instruction you want to find, it would take 10 cycles. So this is a sort of a unified memory, and accessing any data or any instruction will take fixed amount of time, which is more than this if you find it in L1, but it is guaranteed that it is 10 cycles. Okay, does anyone have any question in understanding this real-time system or how to make a real-time processor? So this is what real-time processor is. It gives you a guarantee that work will be done in so much amount of time. It may not be very fast. It's like, it won't finish it in 20 cycles, like, in some best case, your processor of your laptop or your mobile can do it. But it would also not take variable time. It would give you a fixed time.
Hello, sir.
Yes.
Sir, this 100 cycle deadline is for a particular program with particular number of instructions, or should the processor be able to complete the operation for all the programs?
No, naturally it is for single program. And the applications which are done, you don't do a large word processing on a real-time processor. And for that, this kind of processor is better. So usually real-time processor are embedded processors, right? So, and then, which programs are going to be executed, they are fixed. That, like, for example, in your airbag, the program is fixed that, as soon as you get the signal, you send another signal to this chemical bags, and, there is a small explosive charge in that, which would explode. And then, there would be filled up with gases, and, your airbag would inflate. So in real-time processor, the programs are fixed. It's like, your interrupt handlers. Interrupt handlers are fixed, and you can guarantee how much time they would take. And you can do exact calculation, the latency. So as soon as the signal comes to the processor, processor might be sleeping, and we have not talked about that. If you want to talk about it, most of the embedded processors are sleeping. They don't want to waste energy. They wake up when a signal comes from external agency. So in this case, it may be coming from accelerometer, and it sends a signal to processor. So as soon as the accelerometer detects something unusual, that car was traveling at 60 kilometers per hour, and in an instant it came to dead stop. That means it has collided with something. So it would send a signal. So the processor would wake up. Once the processor wakes up, it would start executing the program which is stored in it. And it would go to memory to get the stored program one after the other, and it would start executing. So the guarantee would be dependent on two parts. First is, how long would processor take to wake up and start executing? That is called latency. And then, how long it would take to get the whole program and finish the execution. And, based on that, you can say, this is my hard deadline, that, this program will be executed right from the signal coming to processor to the end of the execution of a real-time program. It would take 100 cycles. You cannot do it for any program, right? Because programs, general purpose programs, can be of varying length. So you can't give a exact idea. So it says one question which is asked is, what if processor take more time than fixed processing time? Well, that means you're not given a real-time processor. Sometimes what happens is that, processor, there is a resource crunch. We saw that, there are problems, why a processor would take more time than expected. First of all, it could have seen this raw hazard, and this raw hazard, one cycle break is compulsory between the two dependent instruction, or there is a branch instruction, and two cycles have to be wasted for a 5-cycle program. But when you are executing a single program, or at the most 2 or 3 programs on a given processor, you have completely analyzed that processor, right? So you know exactly how much time that processor is going to take. If there is a data dependency between first and second instruction, it is always going to be there, and it is always going to take extra time. So you account for that. So in real-time processor, I mean, this is what they have to do. So all automobile processors are real-time processors. I mean, most of the time that, there is a fuel injection thing, car wants an answer within certain amount of time. It can't afford that your processor is hanging. I mean, the processor may hang. General purpose processor, there are more chances of hanging because, suddenly there is because a processor designer doesn't know what kind of program would be thrown at it. So someone has written a program in which suddenly creates a resource crunch. That means structural hazard that, 2 instructions at a time are trying to access a particular thing. Then, it is going to create a structural hazard, and, then the process would hang for a while, or one instruction will have to wait till other finishes. But if the program is a known program, and the processor also, it's a simpler design. It doesn't have superscalar processor like what we are going to study in few lectures. So it is not complicated thing. It's a real-time processors are simple processors because there the premium is paid on knowing the actual execution time. Also, it is given that you have to give a hard deadline. So you don't make the structure complicated. You know which program is going to be executed on it. You know how you have written it. So then you can give guarantee to the manufacturer. But then sometimes accidents do occur. That there is a fault within the processor. That certain contexts. I mean, all these contexts. 3-nanometer technology. So nothing is done by hand. Everything is done by machines. And 3-nanometer wire, if you want to create, it is like maybe 1,000 times the thickness of your hair. So it is quite possible that even few atoms move away, it would be an open circuit, and some of the parts of your circuit will not be accessed. So in those cases, processors fail. But in important things like aircrafts, or in some cases cars or industrial machine, there is redundancy. They put 3 processors, and the reason for putting an odd number of processor is it takes a poll that if one processor starts giving you wrong answer because of some malfunction within the processor circuitry itself, the other 2 processors, I mean, the chances are that they won't be damaged, so they would give you correct answer. So they take 2 out of the 3, or majority decision. Anything else regarding the real-time processor? Okay. So now let us move on to I think these are the 2 things, which I wanted to share with you, because the topic of real-time processor usually is ignored. But, I think you should know. I mean, the processor is the same. The design process is also the same. Only the idea of working is different, that, this has to give guarantee. So it has just one memory, and this is called TCM, or tightly coupled memory. So it's just one memory, and access time is fixed. And for the small processors like ARM7 or ARM9, which you're using, does not have an expensive thing like this, because this is an overkill for a small processor. So small processors are by necessity of this type. That I mean, probably, if you want to design something for, say, healthcare, I mean, how often you want to measure a person's temperature? Maybe once every 30 seconds, once every minute, once every 5 minutes. That's a hell lot of time for a processor. If a processor, even if it is working at 1 megahertz, which is the speed that the processor which was put into Apollo 11 spacecraft in 1969, even that was working at 1 megahertz. 1 megahertz means 1 million operations per cycle. So, uh, 30 seconds or half a minute or a minute is too long a time for a processor. That would be millions and millions of cycle, if not billions, even for a small processor. So, few cycles here and there for an embedded processor doesn't matter. So most of the small embedded processor are by necessity of this type, that there's a single memory, and then there is a small ARM7, ARM9 kind of processor. See, I mean, it can be used as a real-time processor, but real-time processor has to have a lot more than just this. It has to have the guarantee of manufacturing, guarantee of no manufacturing defect, and many other things. So testing is much more important if you want to sell this processor as a real-time processor. But otherwise, many of the low-cost processors are of this type. You don't call them real-time processor, but this is how it is. Single memory and processor. Okay. If this is clear to you, then let us move to another topic. This is called average memory access time. We have been talking about this for a long time, that I told you that in a 5-stage pipeline, 2 stages, that is the fetch stage and the data memory stage. 2 stages are accessing memory. This one is accessing instruction memory. This one is accessing data memory. And this is where the chances are that, you may spend more than one cycle. You may spend, if there is L1 miss and, you have to go to L2, then you will spend 10 cycles here. If you have to go to all the way to main memory, I mean, you will be stuck here for 100 cycles. So you can imagine that your average speed of your pipeline will be totally determined by your fetch stage and your data memory stage. So it is very important to figure out average memory access time. And average memory access time is going to be a determining factor into the speed of your processor. You may say, my processor is like, 2 gigahertz. But, 2 gigahertz is in the best case, where whatever you are looking for, whatever instruction you are looking for is found in L1 cache, and whatever data you are looking for is found in, whatever instruction you are looking for is found in instruction cache, and whatever data you are looking for is found in L1 data cache, then, this would work at 2 gigahertz. But, if there are misses and, you have to go to, say, some other level, then, your performance would start degrading. And that is why it is very important to write a cache-friendly program. Otherwise, if you have written a nice program for gaming, and, if there are lots of misses during fetch stage and more often than not in data access stage, then, nobody would want to run your program. Or they say this game is useless. It's very jerky. That, picture rendition is not good, and so on and so forth. So the question is, how do you find out average memory access time? So this is a very simple formula. And the formula is that average memory access time is equal to time for a hit plus misses into miss penalty, or miss rate into miss penalty, whatever you want to say. So this works like this. Now, time for a hit, even in the best of cases, would be at least one cycle. So when you say time for a hit, it is time, there's a hit is in L1 cache. So whether it's a miss or a hit, you will always come to L1, so you will waste one cycle. So one cycle is here, that is time for a hit. And let us just say that, this is a very simplistic thing. It is just two levels of caches, that's it. There is no main memory. So if the data is not found into L2, it is nowhere. Now, the miss rates to miss penalty. So this miss penalty, you should understand this, that, what is miss penalty? So for L1, miss penalty exactly is equal to L2 hit time, right? If you don't find your data or instruction in say L1, you will have to go to L2. So how much time it would take because you didn't find it in L1? That is exactly equal to the access time or hit time for L2, and that is 10 cycles. So miss penalty of L1 is exactly the same as L2 hit time. So let us say this is miss rate is 0.1%, because hit rate is 90%. I've said you have to read carefully. If I have given you a problem statement, you need to see whether I'm talking about a hit rate or a miss rate. Because if it is in percentage, if I say it's a hit rate is a 98%, that means miss rate is 2%. So to make problem simple, we say this hit rate is 90%, so miss rate is 10%. So that is given as in fraction as 0.1. Multiplied by miss penalty is 10 cycles. So average time for a memory access would be 2 cycles, right? So let us see that 90% of the time it will be done in one cycle, and 10% of the time it will go to the next level. So someone asked this question to me that, why don't you multiply this by 11? And the reason for that is we are taking a uniform time that all data seek or data access or instruction access first has to come to L1 cache. So it spends one cycle in getting here. After it gets the answer that, no, it is not here, then it has to go to the second level. So only those instructions or data which are not found in L1 will have to go to the next level, that is L2. And then, they will spend 10 cycles additional. So that's why it is one cycle plus 0.1 into 10. That means 2 cycles. So look at it this way, that, average rate, hit rate is 90%, and for us 90% is very good. But, with 10% miss rate and, 10 cycles penalty, now your processor is running at half the speed. Previously, it was taking one cycle. Now it's taking 2 cycles, right? Because if even one of the stage is slow, then, all the stages are slow. Is everyone clear up to this point? Okay.
Sir.
Yes.
Sir, if we don't find data in level 1 cache, then
Yes.
we will go for level 2. And
Yes.
sir, then the data which is in level 1 cache will also be in level 2. So it will be means it will be processed 2 times, right?
No. Okay. So this is a good conceptual question. say your processor has sent a request for a particular instruction or particular data, right? So this is now that particular memory address is part of a particular block, right? Now we are talking about blocks. So it would figure out, there is a particular block which is not in this instruction cache or data cache. So it will have to go down to the next level. Suppose the request is for read. That, let's just talk about this data cache, because instruction caches are only read. You never write into instruction. So write request will never go there. For data, you have both read and write. So read operation is like load. You go and read particular thing and bring it back and put it into a register. So that is like load operation. And store operation is like, take some value from here and go there and write into this one. For read operation, it wants to read a particular memory, which is part of a particular block. Now that block is not here. So, suddenly it would say, sorry, I don't have that block. Where would it be? So then, it would go to the next lower level. Once it goes to the next lower level and it finds that block is there. And, since we are saying that this is it, there is nothing beyond L2 in this current system. I mean, of course, in real life, there would be main memory and hard drive and other things. But, I'm making a very tiny system that L2 is it. There's nothing beyond it. So if the block has to be there, it has to be here or nowhere. Or then, it would throw us a illegal instruction or illegal data request because that particular address or block is not there anywhere. So then, this particular block will be brought over here, and then processor would read from it. And, that also takes into account that transferring this block from, say, L2 cache to L1 cache will take finite amount of time. So seek time is 10 cycles. That's what I said, that, going from L1 to L2, 10 cycle is the seek time. So that means you have located the block. Now, in 10 seconds, usually the first batch of the block arrives. So when I say what is first batch, so then, you have to, in real world, you have to have data lines. So in your RTL code, you say, okay, there are 64 lines. You write R equal to 64. That means it will draw 64 lines like this electronically when the circuit is designed. You don't have to do it. The manufacturers do it. Now there are 64 lines and each word is 32-bit. Then only 2 words can go in parallel. Now I have got, say, 16-word block. Then I have to spend 8 cycles. Right? So total time for transfer would be 10 plus the first one comes within 10. I mean, the first pair. So then there will be 10 plus 7. So there will be total 17 cycles will be spent for transferring one block from here to here. So that also kind of, that's why, you are very particular about the size of block. You don't want to bring in too many instructions which are not going to be used. So suppose if you have written a program, and in program, every 8th instruction is a branch instruction on the average. Then you wouldn't want to make your block as like 16 words or 32 words, because that, at some point you are going to have a kind of a branch statement and you will jump up or you will go to some other block. And this rest of the instruction or data in this particular block will be wasted. And so it is also important from this time. So always remember this. When I say 10 cycles to go from here to here, so 10 cycles actually is used for locating that particular block and also bringing in the first batch of the data. And the first batch means how big that batch is. It all depends on how many parallel lines are there. So here there are 64 parallel lines. So that means 2 32-bit data can come at a time. And then in the next cycle, another 2 will come, and in the next cycle, another 2 will come, and so on and so forth. If I had 128 such lines, then 4 words could have come in parallel. Is this clear to you?
Yes, sir.
Okay. So this block size, again requires a lot of thinking. And, there are a lot of, if you want to be a good software engineer for a company like Apple, then these are the things you have to do because, they also make, so you have to think what is the ideal block size. And, there is always exchange of ideas between hardware and firmware designer. If you become a firmware designer, so which is like, straddling between hardware and software, that's one of the most difficult areas. Then, you would be actually determining that, what should be the block size, the ideal block size for a particular kind of work that I have to do. In general purpose, it's very difficult. So, you take some benchmarking program and then determine the size. But, if your work is like sort of known, like, you're designing a graphics processor, then you know that, in graphics, this is generally the size of the block which is required, or this is because, it's a data intensive operation. And, for one instruction, a lot of data is required. It is known as SIMD kind of operation, single instruction, multiple data. So same matrix multiplication thing is used on number of data points because all it requires is matrix multiplication. So this is what happens. Is this clear to you? Okay. So now this is average memory access time is time for a hit plus miss rate into miss penalty. So impact of much larger cache on AMAT. See, we did talk about the graph which you had seen, which was of this axis was miss rate and this was block size. And then, this curves were drawn for various sizes of cache. And we found out that as the cache size becomes very large, the block size does not have too much impact because, too many blocks can be in together because, there is a whole lot of room. So definitely a large cache is great for miss rate, right? So it would definitely improve your miss rate. When I say improve your miss rate means reduce it. But it is the one factor which we had not seen in this graph was what about hit time? If you have too large a cache, hit time will definitely go up with larger cache. So this is what a designer have to consider all the time. That, I want to reduce my miss rate. So what should I do? So the answer would come back to you is, okay, make a bigger cache. Then you'll say, okay, I made a bigger cache, but then this thing got messed up. That time for a hit got lowered, or that means it increased. So then you are back to the same thing. Then someone would say, okay, I want to reduce miss penalty. What should I do? Now miss penalty is then someone would say, oh, make multiple layers of cache. That make a L1 cache and then right next to it is L2 cache, which has got just 5 cycles of penalty, and then another one which another 5 cycles. So instead of just 3 levels of cache, why don't you make 10 levels of cache? That most of the things would be found in L1. Whatever little is not found in L1 will go to L2, but L2 is so close to L1, and then L3, and then L4, L5, and L10. I'm just giving you a theoretical thing. But in that particular case, what we have not yet considered and which we'll be discussing in next couple of lectures is cache coherence is very important. You say that initially a block is written in your hard drive. That problem comes to your main memory, and then it is taken to your L3, L2, and then finally L1. So there is a copy of a block right from your hard drive to L1 cache if it has been used. Now, when you make changes, or when you say write, or when you do write operation or store operation, the processor would change that particular block in L1. Okay, that is fine. But then, suddenly the cache coherence problem would come. Then, other blocks like, your L2 has got outdated value, L3 has got outdated value, main memory has got outdated value, and hard drive has got outdated value. So those values are wrong. And you know that most of the time, uh, uh, if you, since the cache, L1 cache is so small, there is a lot of churning of blocks that, there is not enough space. So you have to throw away some block because of there is a conflict having the same index. And you throw it away and bring in another data or instruction. So what if you throw away something which is there in L1, which has just been refreshed? So then, that calculated value will be lost if you have not written it down into further down levels. So if you have too many levels between L1 and hard drive, then, at some point, you have to update all those values. Why? Because, one of them, the block may be removed either from L1 or L2 or L3. Some block will be thrown away. And, you would be missing out on the correct value if you don't go and, change it right up to the hard drive. So that is something which is known as cache coherence. So that would take too much of a time if there are too many levels. So all this matrix, the designer's problem becomes difficult is, if you go and, try to improve the miss rate, then, your time for a hit would increase. If you try to reduce miss penalty, then probably time for a hit again, would be hit that, it would come down. I'm sorry, it would go up. So there is a problem. Everything would pull you in different direction. The question comes, how can I improve time for a hit? Say from one cycle, how can I make it in half a cycle? The immediate answer would be make your cache very, very small. Then you say, okay, but then what about miss rate? Then, then answer would be, okay, then make your cache large. So then, person would ask, so what should it be? Should my cache be very small or large? Then, you have to make some compromise. And, you say, okay, I made this compromise. I get reasonable time for a hit and I get reasonable miss rate. So that's the dilemma of a designer. Okay. Today I'm not going to do the problem because problem would require one whole day. One whole lecture to do it and to explain it. So I'm going to teach this and, take up the problem. I already mailed you the problem statement and I'll be discussing it in Monday's lecture. Okay, so handling cache misses. So first one is known as read miss. So read miss means sort of like load operation. When you have load operation, you do a read operation. So read operation is done either in instruction cache or data cache. So you read a particular instruction and copy it and get it back, or you read a data and then, copy it into register. Now, what if a particular block is not present in this first level of cache, instruction cache or data cache? Then the answer is you go to the next lower level of cache, see if that particular block containing that particular instruction or that particular data is there, and, and fetch it and put it in its right place, and then allow your processor to read it. If it is not found here, L2, and then if there is L3, or let's just say there is main memory, then you have to go all the way down to main memory. And then, get it from there to there, and from there to there. So then, it becomes a very time-consuming operation. So this is how you handle read misses. There's nothing else to do. If you want to read a data, you read a data, then you come to data cache, this L1 cache. You say, okay, it's not there. A particular block is not there. Then, what do I do? Then memory controller would go to L2 cache and look for that block in that particular cache. Is it there? If yes, then, it would fetch it and put it over here, and then processor would read it from there. So that is how the read misses are handled, both for instruction and data. The next comes is write misses. Write miss means I want to update a value of a variable or value of something, and I want to put it and store that value by using store instruction into this particular block. Now there is no write operation in instruction cache because processor does not change user program, right? So instruction cache only has read operation. This is conceptually very important. You don't go, a processor does not go and write something into your program or changes an instruction or something. That was done by compiler, if it found it suitable, but not by processor. So any write operation, their instruction cache is not involved. It's only in the data cache. So write operation, you can handle it in two ways. If a processor wants to write into a certain block and that particular block is not here, then it can handle it exactly like it handled the read miss. So memory management unit will say, okay, I found it that, that particular block was here in L2 cache. I brought it from there and brought it over here. Then processor wrote into it. And then, that's the end of the story. But then, the question is that, it's not a great idea. Or, someone may complain that, processor will have to wait for 10 cycles that, memory management unit will have to go and fetch this. So it will take 10 cycles to get it. Then, plus additional cycles if the block is too big. I brought it over here and then processor wrote it. So processor was idle for 10 cycles or more. So there is another option. And so this idea of doing like this in a very simplistic way, that if you want to write into a block and if that block is not there, go to next lower level. And if the block is found, get it, bring it to L1 cache, and you allow your processor to write it. And that is known as write allocate. And I've explained that thing. This is write allocate. So write misses is only for data cache. And in write allocate, we stop the execution, fetch the block from next level in the memory hierarchy, install it in the cache, write the word from the processor to the cache, and also update the memory and then let execution resume. So this is a very simplistic way and not very nice, a good architect would say. It says that, why don't you use no write allocate? What it means is that instead of, making the processor wait for 10 cycles till this block is brought here and then, put over here and then only allowing processor to write it, they say use a buffer, right? So processor, whatever value it wants to write, if it is not found here, it will just throw it into the buffer and forget about it. And processor would start executing the next instruction. Then it becomes the responsibility of memory management unit to take the value from this buffer and update it into L2. Just suppose that, if it is there in L2, that particular block. So what we have avoided bringing a block from here to L1 cache just for writing purpose. Here, we are not bringing that block to L1. We are just directly the processor is putting into a buffer, and then buffer through the memory management unit is writing directly into L2. So what's the advantage? The advantage here is that, there are certain values which you change only once in a while. You don't change it very often. It's not like a counter. There might be a particular variable which is just once you write and then, probably not use it again. So for that particular case, it is not a great idea to bring a block from here to here. Because what would happen? because, usually since the data cache is very small, bringing a block from this L2 cache to L1 cache means you will have to throw away some other data. And what if it throws away some important data which is used very often? So in that particular case, there will again be cache thrashing. So in that particular case, write no allocate is a better policy where you don't, the processor does not demand that, this block which is not to be found in data cache should be found from the lower level caches. Bring it to L1 cache, only then I would write into it. No. All it says is, if it is not found in this data cache, I will throw it in a buffer. Buffer is nothing but in a small storage place. And that storage memory then, is contacted by memory management unit, and it directly goes and puts it into the next lower level. So there is no traffic of blocks from L2 cache to L1 cache. So this is what it says. Skip the cache write and just write the word to the memory, but must invalidate the cache block since it will now hold the stale data. So you are changing it over here, and you are putting a flag that this particular thing is a change value. So you are not bringing that over here, and you are saving time. So that is the difference between write allocate and no write allocate. So when I say the word, this is not very clear. I mean, this is a definition from a book, but please try to understand from here that in write no allocate, if a processor wants to write into a particular memory block, if that memory block is not found in L1, then it would tell memory management unit that okay, I have some problem. I'm going to throw that data into this small buffer, and then you handle it. So then it comes and handles it and then updates the L2 cache. So that is write no allocate policy. The second set of policies are there when the data, yes.
Sir, in no write back policy, if we just update the write the value in the memory, then if that block already exists in the lower level caches like L1, L2, and L3, then we also go through these caches that if it is present, then update it like that.
Okay. So that is the next topic. Now the next topic is, this is for write miss. Processor wanted to write something into a particular block, and if that particular block is not found, then there are two strategies. One is write allocate and no write allocate. Now, if the processor wants to write into a particular data and that block is already in L1 data cache, then what to do? So for that, there are two policies, write through and write back. So now the problem is exactly reversed. It is reversed in this particular way. So the problem is this now, that processor, and I'm not putting this instruction cache because writing is never done in instruction cache. So this is data cache L1, this is L2, and this is main memory. Each one of this has a copy of a particular block X. The block X is present everywhere. Now P wants to change a value in X. One of the word in block X, P wants to rewrite or update. So now the question is, as the previous person asked this question, what about L2 and L3? When will you update it? So that is the whole question of writing this policy of when to update the values. So one option is a simplistic option. That is, whenever you change the value in L2, go and change it into, when you change the value of a block in L1, you go to block L2 and change that particular in block L2 and also change it in main memory. Right? So this is a simplistic thing, but someone would immediately say, oh, this is not correct. You are wasting so much time that your processor would be standing idle when all the blocks are corrected. So as time goes, it is not a very nice strategy that you are wasting a lot of time, or your processor is wasting a lot of time till all the blocks are updated. But on the positive side, it's a simplistic thing, right? So you don't require a very complicated hardware to do anything otherwise. And what is that otherwise, or the second strategy would have been? Second strategy says that, okay, change the word, change the value only in X, block X in L1 only. Don't change it in L2 and main memory. And, put a flag, and it is known as dirty flag. So that means this block is dirty. What it means is that this block value has been changed or has been updated, but not updated into lower levels. You keep it there till this particular block needs to be replaced by some other block. So then, if there is a conflict and, the same index, some other block wants to come here from L2 and this block has to go. At that time, this memory management unit will take notice of the dirty flag. And at that time, it would go and write it in L2. Okay. Same thing between L2 and main memory. If some block from L2 is to be tossed away, then main memory management unit will see, okay, there's a dirty flag on L2. And before throwing this block away, first I will go and update this main memory, and only then I will throw this block away. Okay, so then these are two policies. Now these two policies of write back and write through policy and write back policy are applicable only when a processor wants to write into a block and that block is present in L1. And now the only question is, when do you want to update lower levels of memory? Right away? If you want to do it right away, then use write through policy. If you want to wait till that block is to be thrown away, then you say, okay, it's called a write back, that I will update this block only when it is to be thrown away. Otherwise, I will not waste time. Because let's say a counter value. If you have written a program which is just 5 lines long, and counter value keeps changing every cycle, then if you have used this write through policy, then that particular counter has to be replaced in L1 and L2 and L3 and main memory all the time. Then you'll say, oh, this is such a waste of time that every time this comes. Instead of that, you keep on changing in L1, and since this block is used so much, that block will not have to be updated only when the block exits. You exit the loop and you come out. Only then, sometime, some other block may want to replace it, and then you want to write it into L2 and L3 and main memory. So that way, write back sounds like a better policy, but then, you have to have more hardware. Does anyone have any question? So today we have done some important concepts, and I want you to go through it carefully. I also want you to go through the problem statement which I have given you, and we will take it forward on Monday, the solution of the problem which I have given. Does anyone have any question?
Hello, sir.
Yes.
Sir, you say that when we use write through policy, that the processor writes to cache, and then the updates are that on all the lower levels of cache. But then why the processor will sit idle? Because the memory management unit will update the blocks in the lower levels of memory, right, sir?
Well, this is sitting idle is in write allocate or no write allocate. Now processor idle That means because in this particular one, there is lot of inter-memory traffic in write-through policy. That, while it is changing from L1 to L2 and L2 and L3, and suppose if there is a similar demand for some cache memory which has to be brought from L2, then, L2 would say, okay, at the moment I'm busy in updating one of my blocks. Once that block is updated, because, signal lines are common. So whether, it is getting data from this side to this side or sending data from this way to the other way, it has to use the same road. When I say road, means the same signal lines. So that particular way, it would slow things down.
Yes, sir. I got my answer. Thank you, sir.
Okay. Anything else? Okay, thank you very much. So we'll meet again next Tuesday. Sorry, next Monday.
Sir,